Okay, ions, atoms, review. Let's go. So you should be at a spot where you've gone through and completed the lecture notes. This is just to kind of clarify if there was some points that you had missed out on, or perhaps you just like to double check. All those are a-okay. But let's get rolling. So on slide 2, there was a video there that talked about a fellow by the name of Rutherford. And we want to think of Rutherford as the proton guy. Now, why do we think of him as the proton guy? Well, just to kind of briefly recap on what he did, it's freaking amazing. The guy decided to build a device that shot positively charged particles. So he just did that, built something, knew how to do it, made something that shot positively charged particles. And he was curious to see what would happen if he fired this device at different things. So Rutherford aimed his positively charged firing device at a real thin sheet of gold and put a table behind it to make measurements of how these particles would make their way through. And what he figured was some of the things are making their way through. By some of the things, I mean some of these positively charged particles were making their way through, and other times they weren't. So there must be something that allows it to travel through and something that would prevent it. So what he concluded was there must be something that's positively charged within this gold sheet that is repelling some of these positively charged particles that we're firing, and other times maybe we're missing them and it makes their way through. So he was smart enough to figure out that, man, there's something in here that is positively charged. Turns out those were the protons, and sometimes particles can just make their way through. So this is probably made up of just mostly empty space. So that's crazy, right? I mean, if you've got a solid piece of gold, one would think this is solid. But it turns out that the vast majority of everything that exists is just empty space. This pen, hey, Cash, what are you talking about? How could that mostly be empty space? I see it, it's taking up space. That's true. But if you were to look at it at the atomic level, and that's basically what we're dealing with here, you would find that the vast majority of each atom is empty space. And if everything's made up of atoms, and atoms are mostly empty space, that means most everything's made up of nothing. That's kind of crazy. So the slide 3 there, perhaps you've never been to Comerica Park. Think of a Major League Baseball diamond. And you got your baseball diamond. So there's our home plate, first base, second base, third base, back to home. And if you've ever been to Comerica, you know just the scale of this, right? America's a big park. There's the outfield. Let's say this was second base, and we put a penny, 1 cent. You guys know what a penny is. And we put that in the middle of second base. So that penny is going to represent the nucleus. And you should be at a spot now where you know the nucleus is all the protons and neutrons. So one little penny on second base of a Major League Baseball diamond. And then you go outside of Comerica Park, you might find some electrons that were making their way around. So I get that in this example, you might think, well, yeah, there's lots of stuff. There's dirt and grass and the fence and then the back fountain park there by where all the Chevys are parked. Well, this is supposed to be absolutely nothing except for a penny that represents a nucleus. Outside of Comerica Park is where you'd find electrons that are so small in comparison to the nucleus that you really don't even see them. That's insane. That would be blowing up an atom to the size of Comerica Park. So you take an atom, which, there's an infinite number of atoms of ink in this little dot that I made here, and we're going to say, well, let's just take one of those, blow it up to the size of Comerica Park, which is huge, and then we're going to say that basically nothing in between there is anything. There's just all this empty space except for that little nucleus. And then, I couldn't even see a penny sitting on second base if I was on the outskirts where the electrons orbit. That's insane. If I lost you with all that, you got to understand that the vast majority of atoms are empty space. and everything that's made up of is atoms. And that means that pretty much everything that exists is empty space. It's crazy, right? I mean, it sounds philosophical, but it is the way that it is. Could our information or our understanding change? I suppose, but there's an awful lot of evidence to suggest this is the way it is. So, how was Comerica Park used to scale an atom? We're going to say 1 penny for the nucleus, and that's the protons and neutrons, the bulk of the atom, right? And we're going to say electrons, that's my little abbreviation, outside park. What the heck is the most of an atom made up of? Empty space. So we'll get back to that idea, but if it seems weird, good, then you're understanding it. It's crazy weird. Here's what we're focusing on with ions. We looked mostly at neutral atoms in the last lecture. Now we're moving on to ions. Electrons have a negative charge. Protons have a positive charge. If we say something is an ion, it's a charged particle. And it could be positive or negative. So our symbol for electrons, remember we were saying it's a E, and then in superscript, that little negative charge, that's just a way of writing out what an electron would be, or, basically rather than writing out electron. Proton, you can use a symbol of P, and then in superscript positive, because it's positive charge. And now with an ion, I'm just going to put X for whatever element it is you're talking about. That would be the symbol of that atom. And then I'm just going to put like a little circle up top here. Not to imply that it's neutral, but there'll be something that's written up there. So like if I had, let me draw it a little bit larger on my Comerica here. If I had a elemental symbol and you see some sort of a writing, a plus or a minus, that's in superscript in this top right corner, that's saying, hey, this is an ion, and that's what its charge is. So remember, atoms. What the heck are atoms? Atoms are the building block of matter. So could you find different, more concise, more lengthy definitions of an atom? Heck yeah. But we're just going to call them the building blocks of matter. In other words, stuff that exists is made up of matter, of atoms. So what's matter? Well, from unit 1, we said matter is anything really that exists, but we said anything with mass and volume. And then we boiled these guys down to one-word definitions of mass just being space, mass is just being stuff, and then the one-word definition I gave you for volume was space. So if something is made up of something and it occupies some space, it's matter, and matter is made up of atoms. Sometimes atoms bond. So we're going to just say that a molecule is bonded atoms, and we'll get a lot more into bonding in the next unit. But for right now, if you've got atoms that are stuck together for one reason or another, they're going to be a molecule. And we'll see this has an awful lot to do with what's going on with electrons. But right now, I want you to think of an atom as the building block. Sometimes those building blocks connect. You can get a molecule. There's some special atoms that are called diatomic, and they're so reactive, or they really want to be with something so much that a lot of times they'll bond with themselves. So diatomic molecule, man, that sounds sophisticated. Di as a prefix just means two. So a diatomic molecule, that's going to be when atoms bond to themselves. And we've got some cutesy little ways of keeping that straight. In the slide there, you saw Mr. Brinkelhoff, and that'll keep straight what the diatomic atoms are, or the diatomic molecules. If you've got a periodic table, which I should have a periodic table around here, and what on earth did I do with mine is a mystery. Bear with me as I look for it. You'd think this guy would have his periodic table out. So another way of looking at the diatomic molecules is a lot of times I'll call them the diatomic 7. And one cutesy little way of keeping that straight besides Mr. Brinkelhoff, which is like an acronym for these atoms, is you can go to 7, make a 7 down to iodine, and hydrogen. So there's 7. Go to 7. 1, 2, 3, 4, 5, 6. So you see how I kind of like made a 7? And hydrogen. That was how I kept them straight. Or if you take a look at these guys, you've got Br. Let me just kind of jot this down here. Br. That's bromine. Brink. I. N. Br. I. N. Cl. O, F, and H. Whoops, sorry, I should have put H in there. Brinkelhoff, my bad. Anyways, that's 2 ways to kind of keep which ones those are straight. I usually encourage kids just to kind of box these guys off on their periodic table, and then you just have to remember that it's hydrogen, but we'll get back to the diatomics later. What we really want to focus on today is ions. And ions are charged particles. And a lot of times, sorry, spelling wrong there. A lot of times I'll say charged atoms, but usually you use the word atom, like that's supposed to imply that it's neutral. So to say that it's a charged neutral, that doesn't really make much sense. So when I say charged particles, I feel like it's a little bit more concise. And when I just say an atom of something, I want you to think that it's neutral. If you're still not real clear on neutral atoms, I would encourage you to review the last lecture. So electrons, they're huge when we're dealing with ions. And the reasons electrons wander or move about, or sometimes they're shared or sometimes jump, is they want to become stable. And that can happen in a whole host of different ways. But, they're the ones that are moving around on the outskirts. You might remember Bohr. Bohr was our electron guy. And Bohr said, look, you've got a nucleus, and in the outskirts, you've got these electrons that are kind of orbiting around the nucleus. And there's different shells and levels, but this is just sort of a basic, if we've got our protons and our neutrons in there and our electrons on the outskirts, these guys want to either have a full happy shell, which we'll look at a lot more later, or they want to be shared or kind of, jump around, something to become stable. When we kind of keep moving through this, though, if we're looking at the number of protons and electrons in a neutral atom, remember, if we say it's neutral, then that means that your protons equals your electrons, or they're the same. This is all going back to that first lecture. What the heck could be said then about protons and electrons in an ion? Well, guess what? Protons are not the same number as electrons. And you might remember when we got to calculate stuff, we can't change the number of protons. That gives the atom its identity. So how the heck can you tell if an element is an ion? And how could you tell what the charge would be? I'm going to get you to a point one day where you can look on the old periodic table and tell me what the likely charge is of one of these rascals. Today's not that day. Today, we're just going to know that if we see an element that's got its symbol, so I'm just using X as like, a general element, and we see that there's something written up here in superscript, that's the element, and that's what its charge is. And that charge could be positive. So, we might see like this and then positive, or that charge could be negative. And if you just see a positive or a negative, it's implied that that's a +1 or a -1. Cash, what if it says +2? Well, then it's got a +2 charge. What if it's got -2? Well, then it's got a -2 charge. Long story short, if there's some information that's given to you in the top right, or we could say superscript, that's going to tell you what the charge is and that it has a charge. Jumping back from charges, remember Rutherford? He is our proton guy with the old charged particles, and looking at the gold foil, and we'll talk more about that later. But I want to kind of just focus on ions a bit more here. So if we look at what the heck an ion is, I hope you're at a spot now where you could say, Cash, an ion is a charged particle. And I'd say, well, good. When would an ion be negative? And you're probably thinking, I got to look at my periodic table. I forget some of this stuff. All right. Oh, okay. Well, electrons have negative charges. So that's going to be when I've got more electrons than protons. And you might remember way the heck back when I was drawing these crude little teeter-totter seesaw drawings, and I was saying, hey, you put protons on one side and electrons on the other. If I put more over here, that's going to give it a charge that is negative. And if I've got more over here, it's going to give it a charge that is positive. So here's where some kids are going to say something that's going to make me take my shoe off and throw it at them. Well, when would an ion be positive? And they're thinking, oh, I'm too cool for school. If it's negative, that's because you got more of these. So I'll just add on some electrons. And if it's positive, then I'll just add on some more protons. No, no, no. You can't ever change the number of protons. But what you can do is get rid of electrons. And we're going to go through some examples of that in just a sec. But if I say that an ion is positive, I'm going to write down now more protons than electrons. But I want you to keep in mind that doesn't mean I can add protons. Well, if I can't add protons, I got to get rid of electrons. Remember, protons give the element or give the atom its identity. So a neutral atom, well, we've talked about this, right? Think about you jump in a car and you've got, your reverse and you've got your drive and you got neutral in the middle. You're not going forward. You're not going backward. You're just kind of in the middle. So when we deal with neutral atoms in chem, we're just saying that our protons equal our electrons. And when those things don't equal each other, there's a charge, and that's called an ion. And if I've got more negatives, it's a negative ion. If I've got more positives, it's a positive ion. What if they're the same? Well, then it's not an ion. It's a neutral atom. Excuse me. So, atomic number. Sounds like a term I should know. Good thing I wrote that down. Atomic number, that's the number of protons. Number of protons. What does the number of protons determine? The element. I'm going to just put ID. It gives it its identity. Why on earth is vanadium vanadium? Because it's got 23 protons crammed in its nucleus. Oh yeah? Well, what happens if I took one of those protons out? Well, you defied the laws of chem here, right? But then vanadium became titanium. Those aren't the same. Well, why is titanium titanium and vanadium's vanadium? So they got a different number of protons in their nucleus. That's what gives these guys their ID. That's what makes up their, components or their characteristics. So then there was this slide that, I would have walked through with you in class, but we're given some atomic numbers. I know that that's the number of protons. So I don't even need a periodic table to say, well, if it's atomic number 5, it's got 5 protons. If it's atomic number 88, it's got 88 protons. If it's atomic number 16, it's got 16 protons. Oh, okay, smarty pants. Well, what element is it? I don't expect you to memorize this, but I expect you to be able to use this. So if I go 5 protons, atomic number 5, same thing, right? That has to be boron. Always? Yeah, always. That's how that works. What about 88? Who the heck's got 88 protons? Who the heck's atomic number 88? Well, it's the same guy. And if I scroll around, what I'll find is 88 is radium. Always? Yes. Yes, always. That is why radium is radium, because it's got 88 protons in its nucleus. Hence, it's called atomic number 88. Okie dokie. Well, 16 then. I'm seeing the trend. 16, it's got to be sulfur. Abuya. Why? Because there's 16 protons in that nucleus. That sounds important. I should jot that down. Atomic numbers, the number of protons, and I can't change that. That makes up that element. That is who it is because of that. So if it's neutral, what the heck does neutral mean? Well, sometimes I forget in my little tiny brain, so I jotted that down too. Well, I want to have a little reminder that if I say something's neutral, it just means that the charge is balanced, or that I got the same number of protons and electrons. So do I need to look on the periodic table to figure that out? I mean, I got the information here, right? I got 5 positives, 5 negatives would balance it out. If I've got 88 positives, 88 negatives would balance that out. If I've got 16 positives, 16 negatives would balance that out. Or if I had like a little teeter-totter or seesaw, this and this are the same, whoop, it's balanced. Can there be an imbalance? Are they always the same? No, you can have an imbalance. Then you got a charge. That's going to be an ion. You got more negatives than positives, it's a negative charge. You got more positives than negatives, it's a positive charge. No touchy this though. We're going to see we either have to add electrons if we're going to say something's negative, or get rid of electrons if we're going to say something's positive. Why'd you do that? Why can't you touch protons? Because, man, electrons, they can be changed. Protons, they make up the idea of that element. So can you adjust the number of protons? Nope. Never. How come? Gives element its ID. So it is who that element is because of its protons. You can't change that. Can it have some more electrons or less electrons? Sure, sometimes it'll give it a charge, but we can't touch the number of protons. So there's those guys that live in the core, right? We go back to our little Bohr model here. And in the center of the nucleus is protons and neutrons. There is one word that we could use to describe those two real quick, and it is nucleons. Nucleons is just a one-word term for saying what's in the nucleus, or protons and neutrons. How is mass number determined? Well, remember way back when we put down a little cheat about the mass, and we said that the atomic mass, man, that takes into account neutrons. You know, neutrons have a neutral charge, so if we're dealing with ions, we don't care too much about them. When we get into isotopes, we'll see neutrons are important again. But right now, I just want you thinking, okay, well, the mass number, that was the protons and neutrons. So when we were looking at how many neutrons were there, that was like this little formula here, or whatever you want to call it. Hey, if the mass is my protons and neutrons, and I take that mass and I pull out all the protons, I'm left with the neutrons. Changing up things a bit. That was more with the neutral atoms. And again, we'll revisit it with the isotopes. But now we're kind of looking at the ion aspect of stuff. So here I've got some elements. And I got to figure out some information. So I've got vanadium. All right. I got to scroll around on here and try to find where old vanadium lives. Ba-boom. Vanadium lives there. So if I take vanadium and it is atomic number 23, that means it's got 23 protons. And I look at vanadium's mass and it says 50.94. You might remember from previous lectures, I said you got to round this. You can't have a fraction of a neutron or an electron. So if I were to say, okay, well, I've got 50.94, think about it. If you had $51.94, are you closer to $50 or $51? I think we can agree we would call that 51. So I'm going to take vanadium and say, well, the mass is 51. And I can use this information to get my number of neutrons. I take the 51, that's the mass, which, you know, that's my protons and neutrons. And I subtract out the 23 protons, and that leaves me with 28 neutrons. So remember, if you've got protons and neutrons in here, and that's your mass. And then you subtract all this out. And by all this, I guess I should say the protons. Protons gone, I'm left with neutrons. Cash, how am I ever going to remember that? Write it down, man. Neutrons, that's the mass minus the protons. So when we look at that stuff, that is important stuff, right? All right, so now what we got to find is where the heck the rest of our lecture notes are that I've got to put